Hi everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we will be discussing about digital filters. In digital filter, we know that IAR and FIR. So, with reference to that IAR and FIR, the impulse response of the digital filters can be divided into two categories. So, that one is IAR, infinite impulse response. Second one is finite impulse response. Okay, so the impulse response of the digital filter can be divided into two categories, IER and FIR. We will satisfy that IER is IER and FIR, which one is the recursive, which one is non-recursive. Okay, so for this, the formal corresponds to a general case described by the equation below, while the what you call later occurs when n capital N is equal to 0. With this, where the summation k equal to 0 to n ak y of n minus k. Here it is, they are concentrating that ak, what do you call that, ak into y of n minus k is equal to the summation k equal to 0 to m with bk into x of n minus k. With this, okay, so the n value, the into general case described by the equation below, while the what do you call when n is equal to 0. So after that we'll investigate that how is happened that n is equal to 0 or some value. Here it is, we are concentrating only capital N is equal to 0. Here for this, you want to design the digital filter that meet desired specifications in order to get as close to the what do you call ideal filter as possible. Okay, with this, for a best example, for a low pass filter we need to specify the following. Like a low pass filter, it allows only low frequency components, it opposes high frequency components, we know that. With this low pass filter, we need to specify the following, what do you call, like there are several ways of designing h into e power j omega. Like here, that h into e power j omega. To approximate ideal e into e power j omega. Okay, with this, so we will be looking at the obtaining h into e power j omega from an analog filter h into j omega. Using these techniques for analyzing what you call impulse equivalence variance. Okay, next one, bilinear transformation. So for this, we require that some basic knowledge is required how we are designing these digital filters, either IAR, FIR, recursive or non-recursive. With reference to that, capital N is equal to 0. We require that certain stuff is required. Okay, that is some preliminaries on analog filters, like what you call digital IAR filter. You can consider that as to what you call S to Z. Next, impulse invariance information, bilinear transformation. So after that, frequency band transformation. Okay, so because of there is a possibility designing this IAR filters. First of all, what are the stuff that introduction is required? After that, some preliminary analog filters. So after that, once we are having this all stuff related to analog filters, go for digital IAR filter design. How they are designing the IAR filter? There is a possibility using the technique impulse invariance transformation. Second one is bilinear transformation. Third one is what you call under major frequency band transformation. That frequency band transformation, it is under analog domain S to S and digital domain Z to Z. So this is the stuff for designing your digital filter, like digital IARE filter. Okay. With this, we are following the one by one. First, what the stuff, the introduction, some preliminaries on analog filter. After that, we go for design aspects. After that, we have to use one by one, either use impulse invariance transformation or and the binary transformation. After that, we go for frequency band transformation method. After that, we will start to specify that design digital filter design with the help of what we call recursive filter or maybe non-recursive filter. We will decide on. This is our agendas. For this, coming to this one by one, that some fundas or introductions are required. Analog filter. Analog filter, infinitely long impulse response. We know that. Already we learned that under analog filter. Okay, like you can consider a complex valued mapping S to Z. So it is considered that analog filter, infinitely long impulse response. We will consider that S to Z, complex value mapping. With this, digital filter is ready to what you call design, analyze the digital filter, infinitely long impulse response. Okay, but here while you are using the analog filter, infinitely long impulse response. But here while you are using the digital IARE, infinite impulse response filter, infinitely long, what do you call, impulse response. Okay. So, but here both analog filter and digital filter, infinitely long impulse response. How it is varies, how they are interpret with this all distinguish between this analog and digital filters. Okay, for this, so we have to follow this two approaches. Approach one, design analog low pass filter. Okay, so first approach is followed by first design analog low pass filter. It is given to this apply frequency band transformation, that is S to S domain to S. So of that we write to given that apply what you call apply transformation S domain to Z domain. We will expect that our desired IARE filter. This is the first approach. Okay, yeah, there is a possibility for designing this IARE filter, recursive filter. You have to follow. Approach one is design analog low pass filter. The output of design analog low pass filter is given to that apply frequency band transformation. Output of this transformation is given to the apply filter transformation. We will expect that our desired infinite impulse digital filter, infinite impulse response digital filter. This is one approach. If you have observed that are your desirable parameter, desirable responses, okay. If not up to the mark, you go for approach 2. Yeah, in approach 2 is design analog low pass filter. Output response is given to that apply filter transformation. After that, apply given to the apply frequency band transformation. Here it is when compared to this first approach and the second approach, there is a transformation S domain to S domain and S domain to Z domain. But here this S domain to S and here it is to Z. But here it is S domain to Z domain. Here it is Z domain to Z domain. Okay, we will expect that our desired impulse invariant response. Okay, here digital filter response we will expect by using either first approach or maybe second approach. Based on this, we are going to design. This is a major agenda. Next one, what are the advantages using this first approach and second approach by following the different notations here? So major advantage, analog filter design tables available. So already we have seen that while we are using analog filters, The filter transformation is S to Z tables available if you are using this. Okay, this is a major advantage. Next, frequency band transformation, S domain to S or Z domain to Z, it is available. Okay, next coming to these disadvantages. So, no control over the phase characteristics of the IAR, infinite impulse response digital filter. This is the disadvantages while you are designing either first approach and second approach. You will expect this all. You will observe now major disadvantage. No control over the phase characteristics of the IAR filter. We have to justify, we have to analyze, we have to be specific on this what you call phase characteristics of the IAR filter. But that facility is not there. This is a major drawback in IAR filter. Okay, for that, magnitude, yeah, especially while you are using this recursive IAR infinite impulse digital filter, it is only, we have to design only what you call magnitude. But sometimes some applications we require magnitude and phase. But while you are using the IAR filter, we will ready to design only what you call magnitude. There is no phase. This is one more disadvantage while you are designing this type of digital filter, like infinite impulse response digital filter. Okay. Next, other design approaches. So this is the drawbacks or disadvantages we observed. Do we go for other design approaches? Okay. Approach 1 already we know that, the 2 also we know how it is transferred the domain to domain and so on, or the merits and demerits. But other design approaches like simultaneously approximate both the magnitude and the phase response. We go for this, we want to phase response, go for this design approach. Approach 1 and approach 2, there is a disadvantage. How to overcome this one? You go for other design approaches like simultaneously approximate both the magnitude and the phase response. Okay. So here other required advantage optimizations tools and not covered in the SPT, but somewhat it is required. Okay. Next, preliminaries on the analog filters. What are the preliminaries? Some mathematical notations are required, like the analog filter. There may be pass band or stop band, attenuation values, and so on. For this, so the preliminaries on the analog filters here using this tall graph. Okay, here omega versus the magnitude response here. Okay, here the pass band ripple, and here it is A, where the capital A is the stop band attenuation parameter, and the pass band cutoff frequency. That units are, we have to mention the radians per second, and sigma omega s is the stop cutoff frequency radians per second. Okay, like this, HA of omega p whole square is equal on by 1 plus 1 square. Okay, so here right to observe, these are the preliminaries on the analog filters. So analog low pass filter specification, based on this all specification, right to design analog low pass filter specifications here, where RP and AS, where RP is pass band ripple in decibels, AS, where AS is stop band attenuation decibels. Okay, like this here, where RP, we have to follow this all mathematical notation, where stop pass band, the pass band ripple in decibels, 10 log base 10, 1 per square. So this is the we know that all mathematical notation. Similarly, that AS is equal to that stop band attenuation in decibels, 20 into log base 10 A, where A, we know that, where A is equal to 10 power what you call AS by 20. Okay, like this, the analog low pass filter specification is we have to follow. Next, analog low pass filter system function. Okay, first thing, there is analog low pass filter specification is required. Next one, what you call analog low pass filter system function. The system function Hi of s, okay, where Hi of s into Hi of minus s is equal to Hi of omega square equal to s by j. Here poles and zeros of magnitude square, poles and zeros of magnitude square function are distributed in a what you call mirror image symmetry with respect to the what you call imaginary axis. For real filter, poles and zeros occurs in complex consecutive pairs. Like you can consider the mirror symmetry with respect to the real axis. So using this particular preliminaries on analog filter, like analog low pass filter system function HFS is reflected. Okay, analog low pass filter system function HFS, here the what you call poles and zeros will be ready to observe S plane and sigma and j omega and so on. We'll see after this in depth of this analog low pass filter and so on. Here the pickup poles on the low pass and what you call pickup zeros on LHP are imaginary axis HFS, where HFS may be stable or unstable is you can decide. Okay. Now coming to the prototype analog filters. So the prototype analog filters, one is Butterworth, second one is Savishu type 1 and type 2. Like Savishu type 1 and Savishu type 2 filters. And third one is elliptic. Okay. So these are the major preliminaries on analog filters. If you are using this prototype analog filters, you have to use Butterworth, Savishu and elliptic. These are all the popular filters, analog prototype analog filters. Yeah, coming to the one by one, that Butterworth low pass filter, the magnitude square response. What purpose there is Butterworth low pass filter? Try to measure the magnitude square response we will expect while we are using this type of analog filter, like Butterworth low pass filters. This is the response. We'll see after designing this. This is the expected response. Okay, here H of omega square is equal to 1 by 1 plus omega by omega c power 2n. So after designing, we will verify this all are. This is the expected response, but with the pass filter magnitude square responses, the cutoff frequency, we will try to observe that n value order. N is initially n is equal to 1 and n is equal to 2, 3 and so on up to n is equal to 100 and 2 n is equal to infinity. That n is the order of the filter. Next, coming to this Butterworth low pass filter, if it is involved in the system function, the system function is involved. You can consider H of s is equal to omega c power n by LHP poles s of pk. But here it is where we don't know that all pk and s value. S value we know, n value also we know where n is the order of the filters, and this is the system function. But here the low pass filter with the poles where it observed that pk value is new. So for this, where pk is equal to omega c into e power j pi of 2k plus n capital N plus 1 by 2n, where k is equal to, we have to substitute the k value here, the k equal to what you call 0. What happens? How it is, where is that on pk value? Okay, next the k value, that means here it is p equal to 0, we have to verify. Next, where p is equal to, if since that k equal to 0, here k equal to 1, okay, that p1 is equal to, how it is varies, like this, go on, that p2 value, p3 and so on up to 2 into n minus 1. That means here it is the order of the filter, it is reflected with the order of the filter. The order of filter, we say for example, order of the filter is n is equal to 6. Okay, that means where n minus 1. Okay, like this. That means here it is n is equal to 5. That means we have to substitute this all pk k values. What do you call 5? It means where k initially the k equal to 0, 1, 2, 3, 4. Okay, like this. Based on that, we have to verify that pk value. Okay. Next, Butterworth-low pass filter design equations. Okay, here this the design that capital N out of the filter log base 10 of 10 power Rp by 10 minus what do you call minus 1 by 10 power As by 10 minus 1 by 2 into log base 10 omega p by As. Okay, this is the design equation. By using this mathematical notation, this is designed by with the help of the Butterworth low pass filters. Okay, with this omega c is equal to omega p by 10 power rp by 10 minus 1 power whole power what you call 1 by 2 into n, where n is this value, where omega c is equal to omega p by 10 power as by 10 minus 1 power 1 by 2n. This is all Butterworth low pass filter what you call design equations are involved. But here we want to design this all, we have to write a piece of code using this all mathematical design equations. Of that we write to simulate, we will try to verify a Butterworth low pass filter design aspect. Now coming to this distal IARE filter design. This is we will export the test to Z transform. Complex valued mapping, you will try to verify under distal infinite impulse response distal filter. Complex value mappings are next derived by preserving the different aspects of analog filter and distal filter. And your distal IAR filter designs. Okay, now here S plane and Z plane, or how it is varies that where j omega versus that imaginary axis, real axis and imaginary axis, RE of Z and imaginary axis Z. This is all consider this the unit what you call unit cycle. So with the Z plane, put in S plane, so j omega versus that what you call initial that sigma versus j omega, like this. Many to one transformation into e power st into Z. Okay, like that S domain to that S domain to Z domain. So it is reflected. Okay, this Z is equal to e power st. Okay, that means impulse invariance transformation. Okay, after that try to verify that one is impulse invariance transformation. After that we will see that preserve the shape of impulse response. Okay, next impulse invariance transformation. What are the design procedures? Okay, after once we are having this design procedure, okay, go for should write that all what you call piece of code using the built-in or inbuilt function with the help of MATLAB. Like we can consider that MATLAB function is IMP IMEM. This is built-in function. Okay, to choose T and determine the analog frequencies. Next, design an analog filter using the specification. The specifications are involved with the partial fraction expansion. So after that, sometimes it transfer analog poles into the digital poles to obtain. These are all related mathematical notations are involving. Mathematical expressions are involved here. We will verify one by one, like choose capital T and determine the analog frequencies. Where is the T? So we know that all mathematical relations we have to remember here, where omega p equal to omega sigma p is equal to omega p by t, sigma s is equal to omega s by t. Here it is design an analog filter with the system function h of s using the specification where omega p, omega s, rp and as we have discussed. And the partial fraction system h of s is equal to the summation k equal to 1 to n rk by s minus pk. Okay, with the transfer, if you want to evaluate the transform analog poles pk into distal poles e power pk into t into obtain that h of z summation k equal to 1 to n rk by 1 minus e power to pk into t z power minus 1. Okay, like this impulse invariance transformation design procedure. So first choose the t of the design analog filter. Third one is partial fraction expansion and transform analog poles and so on. Okay, after that we will expect that using this all inbuilt function IMPINVR, like magnitude response of analog and digital IR filter. Okay, where blue color is the digital, where green color is the analog. How? Because of you have to write that all piece of code using the MATLAB. Built-in functions f equal to 0 is to 0.01 colon 5 where t equal to 0.1 and z equal to exponential of j2 pif into t, and like this according to this you should write. Okay, so using this all piece of code we have to plot this distal is, so it is going to little magnitude, these are all nothing but here it is mentioned magnitude response of an analog and digital IR filter. This is nothing but what we call impulse invariance transformation aliasing effect. Based on this aliasing effect will be observed. So while designing this one, what are the major merit advantages? The advantages are stable design. Next, analog frequency and digital frequency are linearly related as per this graph. Okay, disadvantages here, aliasing effect is observed here and useful only when the analog filter is band limited, like a low pass filter and band pass filter. Okay, so now coming to the analog filters. Okay, analog filters, Butterworth filters already we know. The under Butterworth filter with the Savichu type 1 and Savichu type 2. Okay, like this filter design technique is involved because of based on the design of discrete time IAR filter from continuous time filters. Okay, so this is the other aspect, design of FR filter by windowing, that we will see that example FR filter design by Kaiser and so on. Okay, now filter design with what you call frequency selective filter past only certain frequencies. Like any discrete time system that modifies certain frequencies called a filter. You know this all. This is the fundamental aspect of this already design. So how it is reflected with the discrete time system. Previous design it is involved through the frequency selective filter past only certain frequencies. Any discrete time system that modifies certain frequencies is called a filter. With reference to this filter, we concentrate on design of causal frequency selective filters. So what are the stages of filter design? Okay, the specifications of the desired properties of the system. They are right to verify that the stages of the design aspects. The approximation of the specification using the causal discrete time system, of that realization of the system. Okay, so We are now right now we are right on focus on this second step, the approximation of the specification using causal discrete time system. Okay, specifications are typically given in the frequency domain. After try to verify. Now coming to the frequency selective filters. Ideal low pass filters are required. You know the background of ideal low pass filter. It is followed by HLP d power j omega is equal to 1 that mod omega less than omega c 0 c less than omega less than pi. Okay. Now the low pass ideal low pass filter HLP of n is equal to sine omega c into n by pi n. The interval minus infinity less than n less than infinity. Okay, so this is the ideal low pass filter graphical representation of this. Okay, so frequency selective filters here ideal high pass filter. This HB of h e power j omega 0 that omega less than omega c 1 if omega less than pi like this, and the ideal high pass filter h of n is equal to delta of n minus sine omega c n by pi n. That interval we have to use this all interval minus infinity to less than n less than infinity like this. Verified. Frequency selective filter ideal band pass filter. It is followed by HBP into e power j omega is equal to 1 omega c1 mod omega less than omega c2 0 otherwise. That's why here it is mentioned these all values in graphically. Frequency selective filters ideal and pass stop. Ideal band stop filter, it is followed by what you call HBS band stop filter in terms of the ideal. Okay, that e power j omega is equal to 0 omega c1 mod omega less than omega c2 1 0 otherwise. These are the frequency selective filters. Using solve filters of that try to design these our distant filters. Within this, the distant filter will be designed with the help of the frequency selective filter. We can consider frequency selector in terms of ideal band pass filters, and before that ideal high pass filter. Okay, ideal low pass filter. Using this all are right to verify this. These are the stages of the filter design. Okay, you have to follow this all step, this specification of the desired properties of the system, the approximation of the what you call specifications using the causal or casual discrete time system, the realization of the system. With this, specifications are typically given in the frequency domain. So how it is reflected? This using this all steps 1, 2, 3, 4, 5. 5 steps are required for the stages of the filter design. Using this all 5 steps, user can expose that a distant filter is maybe it is desirable value, or if it is followed by first approach, if it is suitable for approach 1 or maybe approach 2 or other approaches, you can design your distant filters. Okay, this
Like, share and subscribe. Hit the bell icon for more updates.